Good afternoon, and welcome to today's Utility Analytics Institute webinar titled Empowering Utilities, a Holistic Approach to Resilience and Reliability System Planning, sponsored by Gurobi Optimization and Quanta Technology. I am Gina Weber, Managing Director of Utility Analytics Institute with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit those to the question window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during the event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to enter those questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Utility Analytics Institute website in the next 24 hours. You'll be notified by email when the archive is available. Now I'd like to introduce our speakers for today's session. First, we've got Ani Sadikovic, is the Senior Director of Quanta Technology. Shanshan Ma is an advisor with Quanta Technology. Zahara Sultani is the Senior Engineer at Quanta Technology, and Jason Morris is the Account Director of Gurobi's Optimization, Power, and Utilities. Welcome, panelists. Jason, I'm going to turn things over to you.
Thanks, Gina. I just wanted to give a quick introduction. So Gurobi Optimization is sponsoring this webinar because we're focused on delivering the best solver in the industry. And as the Account Director for Power and Utilities, I'm driven to expand the adoption, accessibility, and awareness of optimization for better intelligence, decision intelligence in the utility industry. Our partners deliver the end-to-end solutions that are really used by the end users. And Quanta is one of those that we're really impressed with the innovative technologies that they're utilizing Gurobi in. And for that reason, we're sponsoring this webinar so they can dive in and give us a deep overview of this application around reliability and resiliency, which everyone in the industry has probably heard that term quite a bit over the last few years. So with that, I will turn it over to Ani, and we'll kick off the presentation.
Thank you, Jason. Pleasure to be here, and thanks everyone for joining. I promise you the next hour will be well spent. And we are happy to be here with Gurobi, who's been our really good partner on this journey. I don't see presentation on my end. Are we sharing the slides? Excellent. All right. All right, well, let's get it started. So let's go to the next slide, please, Shanshan. Next slide. All right. So today we'll kind of focus our discussion around three main topics. Number one is going to be discussing what and why have we done on the topic of resilience and reliability planning. We will also focus a little bit of our time talking about the optimization functions, and you'll see some constraints and complexities that all brings and how we use Gurobi to address those complexities. And lastly, we'll show you some use cases so you can see what kind of results we achieve when this sophisticated process is put in place. Okay, let's go to the next one. Thank you. Before we start talking about resilience and reliability, a quick introduction on Quanta Technology. For those of you who are not very familiar with Quanta Technology, we are a consulting firm and technology provider to electric utilities. The company has been around for 2 decades, give or take. Almost 400 people in the company now. Lots of subject matter experts, lots of folks with really high education, subject matter experts in respective areas, tons of papers and books written, patents that we hold. So Quanta Technology has been really, you can see innovation written all over Quanta Technology's history. And that was partially success to, that was an important driver to our success in the industry. Quanta Technology is owned by Quanta Services, which is a publicly traded company on the New York Stock Exchange under the ticker PWR. And Quanta Technology has been a major driver to Quanta Services' success. Okay, next slide. All right, so on the topic of resilience, so I don't mean to make this a philosophical talk about resilience, but I just want to kind of give you a sense of why we have to start looking at things differently. So resilience, in essence, the way I like to put it is that, there are 5 fundamental principles that we go about when we talk about resilience. So projects, plans for areas, it really boils down to using these different drivers to enhance resilience. So we have to provide some flexibility for the system. Operational flexibility matters. We have to have redundancy, especially for critical assets. Diversity is extremely important, especially with these extreme events. No one keeps 401k portfolio in the one basket, so the same thing applies here in the portfolio design for resilience. Robustness is critical, so we got to make sure that the system is robust enough so it can withstand the impact. But really, the essential piece is affordability. And when we start talking about affordability, this is where tables turn a lot, right? So right now, or traditionally, how system planning has been done is that there will be a bunch of different activities driving improvements with the objective to improve resilience performance. And then at the end, all of these activities are kind of met together, and we combine all the proposed upgrades. And what happens usually is that the dollar amount that's being stitched together exceeds what's affordable or available in the budget. So that process on its own is not quite efficient, and it definitely gives a suboptimal performance of the system and use of capital. So what we've done is, but the reason it was done this way is simply because that's something that is solvable. That's something that we as humans, we break down problems into smaller problems, and then we simplify some things, make some assumptions, solve them, and then bring it together and do our best what we can. But if we really want to do optimal capital spend, then the formulation of the problem has to be different. The formulation of the problem has to be, I want to design the most affordable solution that addresses all these demands, all these requests that we put in motion, and they come in different activities, different asset classes, and things like that. The problem with that is that that's not something that human brain can comprehend. This is where Gurobi comes in play and similar software. So the optimization problem that we have to deal with is extremely, extremely complex, especially for resilience. So you'll hear from us as we go through this presentation, and by the end of this presentation, I believe you will be convinced that when it comes to system planning with resilience and reliability, we have to be rethinking how we approach this and relying more on optimization tools. Okay, next slide, please. All right, so the way really process works for resilience planning is we have to define what are we trying to design system for. So for example, we can be designing system for, to best handle hurricane impacts or wind, ice events, things like that. So that's kind of the environment that you'd want a system to operate well. There are also a bunch of complexities coming into play. This is where psychology matters and what's going on, the history that happened there, what kind of customers, utilities are serving. So there is a need always to pay attention to some things more. You may have some sensitive customers we got to deal with, right? So that has to be de-risked properly. But ultimately, in terms of optimization, we are talking about the following. We are saying, I want to minimize investments today and in the future. And I also want to minimize my operational cost or utility operational cost. And also want to minimize societal costs that society may incur as a result of loss of power. So this is kind of really nicely said, the sentence, but really the objective there is, if we can solve this or for that, then we are bringing decision-making in the round of, okay, so now we have enough information, compiled information, so that the decision makers can decide where to move capital, right? And understand the trade-offs and returns. So I'll give you an example how that looks. So can we go one more step? Excellent. So let's say that we have a system that has certain performance in terms of resilience. And this is what you see there is resilience curve. For those one who are not familiar, on the left-hand side, we have percentage of power served, and then on the x-axis, we have time. So what's happening here is we have system as is, and we try to see what kind of things we can do in the optimal fashion to enhance the resilience, which means we are shrinking this curve as much as possible. So in this case, for example, we can rely on drive one of the fundamental principles, which is hardening, and say, well, we want to do distribution, let's harden the system, let's harden the distribution poles, and that brings your resilience curve to one better place. But we can say, let's pull another principle, maybe let's try to build in flexibility, and we start putting sectionalizers. We improve resilience curve even more. Then we can even introduce some of the diversity and start putting some storage or 4 microgrids and things like that. So you see how this all comes together, right? But trying to find the most optimal solution for a series of different outcomes is extremely complex process. And this is where optimization comes in handy. Okay, let's go to the next slide. We'll cover quickly reliability problem, right? So typically what electric utilities do is they try to do the best customer segmentation to really best perform in terms of reliability indices, which is usually SAIFI and SAIDI. This is what regulators are asking utilities or measuring utilities how they perform. So that's what we get in return, right? And of course, nowadays, we don't really have necessarily optimal reliability planning process. There are some ways how reliability is improved, and this is, nothing new. Utility has been doing this for a very long time, but we will show you what kind of challenges actually are utilities facing when it comes to even doing this, which I want to call like the default approach, and how important it is to use optimization in it. Okay, so that's the customer segmentation approach. But what's the problem with customer segmentation? Not every customer is the same. So if you have a commercial customer losing power for 4 hours, and you have a residential customer, SAIFI performance kind of treats that customer the same, but I'm pretty sure that the commercial customer owner would disagree with that type of approach. So there is an approach where we call load segmentation, where we are trying to maximize dollar savings per customer interruption avoided, customer minute avoided, and that those dollars are different for different customer segments, right? So that's another approach that we take sometimes, and this is usually we do with customers when there's some kind of significant or important commercial or industrial loads on the circuit. And the last one here is kind of the most advanced and probably the most interesting and challenging to do, and that is planning for some type of uncertainty. So we know the failure rates, we know historically how system performs, we know where the risks are, but looking kind of in the future, we are really, there's a lot of uncertainty. You know, we can talk about additional load growth, electrification, and things like that. Once you start designing the system for reliability, you essentially what you're trying to do is to enable ADMS, for example, to be able to move loads around, so to play with that flexibility as much as possible. So it's a little bit different formulation of the problem statement or objective function, but these are kind of covering like all three kind of different approaches to doing reliability planning. So let's go to the next slide. And so what this brings us nowadays, right? So I think the process, how we do planning, kind of doesn't change. We still have the same steps. We set up the system, we do the setup, prepare the models, model risks, do all the things, right? We got to do we go through a system planning process or system design, whether it's reliability or resilience, find solutions that best address those challenges. We have quality control aspect and then quality assurance. But really what's happened over the years is we kind of enhance these processes by going from kind of doing work manually to automating some of this work. And then we realized that's not really doing the job that we really need in terms of maximizing return on invested capital. So we tried to look at the best ways to do that, and we realized that we don't have really the good resource allocation here. So we've shifted from engineering and automation to kind of engineering and use of machines, call it, right? So those are kind of our major shifts now that are happening in our industry. And right now, in solution design, so whether we design a system for reliability or resilience performance, this is all done by machines. So it's a streamlined process. We call it augmented intelligence because there's some physics laws that has to be satisfied there. Things can't be made up. But this was a huge shift now, having machines doing all this work because they're much better at it than humans. Also, we are seeing enhancements that we can do in terms of quality control using some of the artificial intelligence, mainly in the domain of large language models. But these are kind of the major shifts that we are seeing now. And Gurobi has placed in solution design critical place for us. Can we go to the next slide, please? Okay, so these numbers that I'm showing you here, it's actually with respect to reliability planning assessment, because resilience is even much greater success, but it's really hard to measure what we gain in return with these sophisticated processes that I just talked about on the prior slide. So what we are able to do is tremendously improve the throughput. So the time that it takes us to turn around 100 circuits per plant, and the reason we're doing 100 circuits is because they can't take more and do acceptance testing, is because of this sophisticated process, the use of machines and Gurobi and optimization frameworks. We are able to do at least 50% cheaper. It costs us at least 50. We can save our customers at least 50% in terms of costs, what would it take utilities to do work internally. And our labor is, so far we are seeing, I think conservatively, we can say 3x reduction in labor. And these are all challenges that our industry is facing: lack of resources, lack of time, the turnarounds are quick. Everyone wants things done in a month or two for a good reason. So just emphasizing how important it is to really embrace and move towards this new process where we allocate these resources appropriately between humans and machines. And with this, I'm going to pass to Shanshan, and we're going to start talking about the framework and how we put these optimization functions together. Shanshan?
Yeah, thank you, Annie. To improve the system's reliability, we developed a decision maker solution to help two utilities to place reclosers. We consider the filling rate uncertainty and the switch operation. Here, I want to explain what the recloser is in the power system. Recloser is one kind of the protection device. It can automatically detect and interrupt the electrical faults in the distribution system. Once the fault is clear, the recloser also can re-energize the circuit. In our model, we formulate the problem as a two-stage stochastic mixed integer program. In the first stage, we try to identify the recloser placement location based on the utility's requirement and the engineer's practical experience. In the second stage, we simulate the switching devices operation when the line fault happens. Here, based on the utility's self-healing ability, we formulate two sub-models. In the first model, we assume that the utility has the self-healing and operation ability. That means the protective device and the tie switches can work together at the same time to isolate and clear the fault, and then also transfer the load. And in the second sub-model, we assume that the utility do not have the self-healing ability, so it will follow the traditional switching operation steps. Firstly, the protection device like the fuse and the reclosers will open, and then the crews will arrive the manual switch locations. They will try to open the manual switch to clean the fault. And finally, the crew will try to close the tie switch to transfer the load as if possible. And in our first stage of formulation, we can see that our objective is to minimize the expected value of the second stage in the realized line fault events. Here, we use the predetermined number of the reclosers. This is based on the customers or the number in the system. And to coordinate the reclosers communication in the same path, we set the number limit for the consecutive reclosers in the series. So usually the default number limit is 4, but it can be adjusted based on the utility's requirement. And this, also we try to satisfy the recloser protection requirement. We consider the fault current difference constraint for the recloser in the series. For example, if the fault current between the reclosers to the feeder head should be more than 30%, and the fault current difference between two series recloser, it should be more than 15%. Those percentage setting also can be adjusted based on the protection requirement. And as we know that reclosers are commonly used in the overhead line, so we set a constraint to only place the recloser at the overhead line sections. If there is a regulator in the feeder, we won't place any recloser at the upstream or the downstream of the regulator in a specific distance. The most important thing for the recloser placement is how to do the customer or load segment for the different recloser zooms. In this, we set up the different lower bound of the customer or load number for the recloser zooms with different devices like the feeder head, existing reclosers in series, and but the most challenging thing is that we need to, when the network becomes complex, how we set the customer or load segment requirement for the reclosers. They are at the different branch. We think this problem we divided it categorized in the two groups. One is if the number of the recloser is greater than 2. we need to set up a set of constraints to think about the circuit breaker zoom's lower bound, how to satisfy this, and also when the recloser number is greater than 3, we need to model a set of the constraint to set the lower bound of the customer load number for the recloser zone 3. If we do not set it, we will see that this recloser zone, they have very low number, and this will make our recloser placement is not so valuable, as we know that the recloser are very expensive for utilities. Yeah. In our second stage, we also we will try to minimize the SAIDI or the SAIFI in a realized line fault event, giving the recloser placement locations. As the recloser location decisions have been fixed as a parameter, we need to consider when a fault happens, on how the switching devices will operate. We model 2 sets of the constraint. One is the disk flow constraint, which models the 3-phase unbalanced power flow. It considers the voltage limit, thermal limit, power flow injection, power balance, and the KVL constraints. And the other set of the constraint, we consider the switch operation constraint. It will simulate the outage propagation. When there's a fault happens, the line will be out of service and the fault will propagate until it meets the protection device as like the recloser or the fuse to isolate the fault. And also we have the loop isolation constraint to keep the network as radio, and the load shedding ratio constraint to guarantee that if the load connected to the out of service lines, the load will be automatically out of the service. Now I will pass the results part to Zara. Yeah.
Thank you, Shanshan. We have implemented our proposed optimal recloser placement algorithm on more than 1,000 feeders across 2 United States utilities. Each of these feeders and utilities has its own characteristics and challenges. Some feeders have a lot of underground lines, some feeders serve mostly industrial and commercial customers, some feeders are very long and serve a lot of customers. Managing all of these complexities manually is very hard, and that's where optimization comes into play. We need an advanced automatic approach to handle diverse feeders with different characteristics efficiently. Next slide, please. Let's look at an example how our optimal recloser placement algorithm works. We are looking at a small feeder that serves about 1,300 customers over 24 miles. In figure on left, you can see that currently there are no reclosers in current topology of this feeder, a configuration we refer to as brownfield. And our objective is to identify optimal location for reclosers to minimize SAIFI. And you can see in right figure that our optimization algorithm proposes addition of 2 reclosers, which are marked by red star, to decrease SAIFI. And on top of the slide, you can see that not only has SAIFI decreased, but SAIDI has also decreased in optimal scenario compared to brownfield case, which represent current topology of feeder. Now let's look at number of variables. Yeah, same slide, please. Now let's look at number of variables involved in analyzing such a small feeder. We are dealing with about 94,000 continuous and binary variables for this small feeder, which I believe human brain cannot comprehend all these decision variables simultaneously, let alone solve optimization problem and accurately assign value to these variables. Next slide, please. But complexity of this optimization problem doesn't end with having many decision variables. We are also dealing with several constraints. Some of these constraints are particularly favored by our utility company customers. For example, let's look again at that simple feeder example. our utility customer owning this feeder prefers a segmentation of 500 customer along feeder with a flexibility of plus or minus 20%. And you can see at bottom of figure where red boxes are that our optimization algorithm has segmented customers in a way utility company preferred. We also have to deal kind of with a lot of practical constraints. For example, fault current difference between protection devices should be more than 30% to ensure proper protection coordination. But here, I've just scratched surface of our optimization model with just two constraints. Next slide, please. Next slide, please. We have to deal with many additional constraints. So those constraints that I showed in previous figure, slide, are not only constraints. We have to deal with many additional constraints. On top of that, we have to deal with lots of variables, and wow, too much to handle by human brain, right? And that's where our hero in this story, optimization, comes into picture. We believe optimization is only way to solve such complex problems. And to solve such complex optimization problem, we need a robust and capable solver, right? And we need an optimization solver which is not only accurate, but also fast, and it's not gonna take forever to solve such complex problem. And that's why we've chosen Gurobi solver for solving optimal recloser placement problem. It's because Gurobi is capable of handling optimization problem with a large number of binary variables and constraints, both accurately and quickly. Next slide, please. But maybe, I don't know, some of you are still unconvinced by earlier slides, doubting whether such complexity exceeds capability of human brain or not. And then let me show you another example. This is a large feeder serving about 5,000 customers over 47 miles. And just look at the number of variables involved here. We are talking about 2 million variables for just this small feeder. I mean this feeder alone. And this is not an uncommon scenario. Many utilities deal with such complex feeders now. And this is exactly where power of our optimization algorithm become evident. Our optimization algorithm could handle all of these variables and constraints, and you can see how our optimization algorithm strategically relocates certain reclosers from current topology of the feeder in left figure to optimal position in the right figure, and decreases SAIFI and SAIDI metrics, which perfectly, aligns with our objective. Next slide, please. Here is another feeder with about 6,000 customers. In current topology of this feeder shown in left figure, there are no reclosers installed, right? And then in top of a slide, you can see current topology, which we refer to as brownfield, has high SAIFI and SAIDI values. And since our objective here is minimizing SAIFI, our optimization algorithm strategically places reclosers to enhance reliability and reduce SAIFI, which also decreases SAIDI. And you can see on top of a slide that SAIDI drops from 6,000 to almost 1,000 in optimal case, which is about like six times improvement. And similarly, there is about 6 times improvement in SAIFI. For this problem, we can see that there are about 1 million variables, and then we have also many constraints. And yet, our optimization algorithm efficiently handled all complexity and successfully met our objective. Next slide, please. I'm just going to pass it to Ani now. Thank you.
Yeah, for us, For this resilience, we come back to the resilience design. In the resilience design, that we try to make our distribution systems more resilient against the extreme weather events. So we also developed a stochastic decision process to optimally harden the line, place the backup distributed generator and sectionalizers and we consider this special temporal correlationships with of the planning decisions and the uncertainties, which induced by the extreme weather events. In the uncertainties, we can see that the line damage status are determined by the wind speed, pore stress, and the repair time. All of them are unstochastic. In particular, if we the pore stress and the repair time are decision dependent, it depends on whether we harden the line or not. If we harden or upgrade the line, the pore stress will become stronger and it will be hard to be damaged. So in this way, the repair time will be also reduced. And in this uncertainty, we also consider the demand, the load demand, and is uncertain under the extreme weather events. In the second stage, we model the distribution systems operation during and after the extreme weather events. This model can capture the impacts of our planning decisions and uncertainties on the system's response to the extreme weather events. And this, as we formulate as the two-stage stochastic mixed integer program, also we implement this formulation in the utilities feeder, and for the result, we also validate our system reconfiguration result in the synergy to check whether our model can improve the system's resilience or not. And I will pass it to Annie to show the result here.
Yeah, thank you, Shanshan. So as Shanshan outlined, there is kind of a series of kind of snapshots that we capture throughout the process of what the outcomes, expected outcomes are during and after the event, so during restoration stage. So you can think about like stringing all these snapshots together and at the same time identifying problems and solutions, right? So this is a very unique approach where traditionally the system planning is kind of like two-part process. The system impact study is done, and then we see what kind of problems we have, and then people talk and figure out what the solutions are, and then go through like verifying that all mitigates the problem and whatnot. So the beauty about this process is that through use of OPF and of course Gurobi optimization in our framework, we kind of handle both of those aspects together. Computationally, it's the extremely superior process compared to anything that's being used in the industry today, regardless what kind of automation processes are used. For some very complex problems on resilience side, it may take, a few hours to maybe several hours, or maybe even for some complex problems longer. But that's a computing time trying to condense all these kind of problems to come up with a solution, right? So in terms of resource utilization, that's really important to consider, and putting the right use of resources, in the process. But nevertheless, back to this design here. So this is an example of three circuits. This system is in a pretty bad shape to start with. It has a lot of class 4 and 3 poles, I believe, if I remember well. So it's not surprising to see such a big difference between where we started, which is the red line. You can see the resilience curve and also number of poles with high risk failure that we are experiencing in the throughout the process or the event. But the way this system works is really when we identify solutions, there are a number of risks here in place. So every asset that you see here, or every pole, for example, every distribution pole has its own risk failure model, as other assets do. So a bunch of risks are represented in the model. If an asset reaches certain threshold in terms of failure risk, that asset will be considered to go out of service. And as it goes out of service, the whole switching block goes out of service. If any load transfer is possible at that moment, this is all expressed throughout the optimization, through the OPF, and staging these frameworks or snapshots. So that's how we develop what we call forward-looking resilience curves. Building resilience curve or using historic data is easy, or it's doable, right? Creating forward-looking resilience curves, what's expected, is extremely complex process, but it's necessary for resilience planning, and this is what our process does, right? So in this case, for example, we would determine what kind of assets need to be hardened or not to be hardened, where to place sectionalizers, and understand how to use those, load transfers throughout the process. Okay, next slide, please. So at the beginning, we started off discussion about decision-making and how to deploy capital. And I made a remark that usually the problem is that we have too many dollars competing for the budget. Once we turn that and we start looking from our affordability perspective and trying to design a system from that perspective, it becomes very transparent that doing something with the system is better than doing nothing most of the time. So these numbers that you're seeing here, please, folks, this is all just simulation. We just made some assumptions for operational cost, restoration cost, outage costs, and things like that. So please don't take these numbers off the books here. The point here is the following: whether we design system for, let's say, 130 miles per hour, or 80 miles per hour, whatever the design criteria is, you can see on as-is line, whether you look at one circuit or you look at 2 circuits or 3 circuits, you come to the same conclusion, that leaving system as is, you're saving money today on our investment front, but you're going to be incurring a lot of cost in operational terms for utility, and also silent cost. The question is, how do you engage in these mitigation efforts? So just for the sake of discussion here, we are showing if we take one strategy, which is like hardening the poles, you can see we are getting improvements in the far right column. You can see the total cost that's expected, and it's lower, right? So if we engage in multiple strategies, the more strategies we add, the more degrees of freedom we add to the solution, and we can get a better system design that overall is more cost effective, and it has better ROIC than other solutions, right? But again, getting to these solutions is, we need a process like what we've described. There is no workaround. And of course, there are challenges with this. Skills are needed. So this is where, it takes particular skill set, like, skills that Shanshan and Zara have, working with optimization functions, understanding complexities, and then identifying the right software optimization solutions. Our choice was Gurobi for the reasons that you heard, but it's necessarily needed, sophisticated optimization tools are needed. These complex problems are extremely hard to handle unless you have these sophisticated tools. Okay, let's go to the next slide. So we talked about resilience and reliability, but I just want to make it transparent to the audience here that we use Gurobi for, different applications as well. Whether we try to address the problems of non-wire alternatives or electrification problems, this is all handled with use of Gurobi for pretty much same reasons what we've discussed. There's a lot of decision variables, a lot of constraints, a lot of power flow laws that have to be, complied with, and limits to be honored. There's a lot more we can say on this topic of use of Gurobi, but definitely when we look at the whole utility space moving forward, especially in the regulatory environment, we definitely see optimization and process of vetting solutions through the lens of optimization as something that's really unavoidable, and it should become definitely a new norm. And I want to leave you with that. So you can go to the next slide. Optimization system planning, or optimal system planning, is here to stay, and it's going to be more transparent. And we as an industry have to work together more to make sure that it's adopted properly, and also with the industry to understand the benefits and trade-offs if we don't end up going toward this optimization path. With that, I want to thank you, and we can open for questions.
Awesome. Well, a few of you have already submitted questions. In fact, we've got quite a few, so we're going to jump right in. But as a reminder, if you'd like to submit a question, just type that question into the question window on the side of your screen and hit submit. And I will get started with the first one. It says, are you modeling the nonlinear AC power flow constraints? If not, would that be valuable to include?
For current model, we are using the linearized, the flow power flow constraints. So we do not consider the nonlinear one, because this will make our planning problem too complicated for solving the problem. Yeah.
Okay.
And now that for the flow, it's already reached to the accuracy. Accuracy is very good for the planning problem. That's why we only consider the linearized power flow.
Okay. On the next question, it says, did you have to employ certain strategies to deal with massive number of integer variables in the model? And did you have to change Gurobi settings too?
And for this optimizations model, we give some the default parameter settings, such like that I mentioned in the first stage, like the number of the reclosers, or the number of the reclosers limit for the consecutive reclosers, and the percentage of the lower bound for the customer segments. For those are the parameters that were based on the utility or the engineer's practical experience. It can be adjusted. Yeah.
Okay. Moving on to the next one, we've got quite a few to get to. The list is still growing, so I'll keep going. It says, what is the type of problem you solve? Like, for example, linear or nonlinear MIP, how many optimizations do you need to run and how fast? And then another question with that, same one, is what type of help from Gurobi support did you get in the integration of Gurobi Optimizer to your system?
As I mentioned in our presentation, this problem we formulated as a two-stage mixed integer programming. So in this problem, we have the two kinds of the variables. One is the binary variable to make the decisions and decide our land status and the load, whether we need to shed the load or not. And another is the continuous variables to decide our like the power flow, the busing and power injection and the voltage, those continuous variables. And for the computational time, it will depend on the complexity of the feeder. Some feeders, as we have it's very small feeder, so it will maybe takes like a few 100 seconds to finish it. But for some large feeders, maybe it takes around like 1 hour, which include loading the data into the model and then solve the problem. The total time will be around 1 or 2 hours. It will depend on the model's complexity and the scenarios we gave for the uncertainty. And for the group. And the Gurobi, actually, from our practical experience, as we processed more than 1,000 feeders, and the Gurobi provide a very strong processing ability for the mixed integer problem. That's why we choose the Gurobi to process.
Awesome. Thank you, Shanshan. The next one, and this kind of, I think, is related to that, but it says, how long did it take Gurobi to solve this model with million variables, and what is the stopping criteria?
So for that one, I think, as Shanshan mentioned, we have a time for reading the data for like feeder, and then we have a time that like Gurobi takes to solve it. I think for the time that Gurobi takes to solve it, it's like, I think for that one that has a million variable, it was about, I think 20 minutes for Gurobi to solve it.
Nice. Okay. The next question is, how is there an exponential increase in the number of binaries with a few increase in number of recloser decisions? Solver can only do so much, and I believe that the major challenge is to model efficiency rather than letting the solver do its job on any optimization model. And are you thinking about alternative modeling techniques to reduce modeling complexities?
For us is that we continuously revise our optimization model to reduce the variables, and but for some complicated network, if we see that in my models, the most challenging part is that how we model if the reclosers at the different branches, and then based on this, before we start to solve the problem, and in our model, actually we do lots of the graphic graphic related functions to make our network to be more simpler and to reduce the complexity of the model formulation for the reclosers. Yeah.
And there's a second question to that. It says, hardening and switch investments are more of a long-term planning problem. Is the planning based on time series simulation, or is the time series results more of a validation?
For this resilience design, this problem is that we consider that is like the 10 years the feedback, and we will consider that in this 10 years we consider the different probability of the hurricane will come to hit the system, and we use this one as the uncertainty to get like more than 10 or 30 scenario, depends on the feeder size, and in this way we to formulate the problem. We do not use the time theory to consider it. Yeah. But we consider the whole process of, in the second stage, we consider the whole process from when the hurricane or other wind extreme weather comes until this whole system be repaired to back to the normal operation.
Thank you. The next question, it says, does inclusion of 55,000 or I think it's 1,851 binary variables significantly impact the runtime of this model? If so, how did you address the issue to expedite the runtime? Let me read that question again. Did I stump y'all?
Yeah, can you read that question again? Yeah.
Yeah, it says, does the inclusion of 55,000 or over a million binary variables significantly impact the runtime of the model? If so, how did you address the issue to expedite the runtime?
Yeah, sure. It definitely impact the runtime of the solver to run it, but that's why we are using Gurobi, because Gurobi can efficiently handle all of these binary variables very well, and then we can get a solution fast. It's not gonna take, forever. It's as I mentioned, for that one with 1 million variables, combination of binary and continuous variable, it took about 20 minutes. So that's why we are using Gurobi. It's really efficient and fast.
Yeah, and also at the same time, if that for our problem, it cannot be solved in the 2 hours, and we will go back to check the network, the feeders network, and to see whether there's maybe there's because some the specific thing for that feeders network, and we will go back to check our model again to see whether from the model we can do other things to make this problem to be smaller.
Yeah. Okay. Is the full optimization model with millions of variables given to Gurobi, or are you using a decompensation approach?
Currently, we do not consider that because the Gurobi already can give us a very good result for the utilities feeders. Yeah. If later, if the problems, if we meet the more complicated feeders, we may consider that. Yeah.
And also we have some network reductions approach that we already have in our algorithm. If needed, for any feeder, we can use that. But so far we didn't see that kind of problem to use network reduction.
Great. Moving on to the next one. We've got time for maybe 1 or 2 more. Could you provide insights into key challenges utilities face in implementing sophisticated approaches to resilience and reliability system planning? And how are these challenges being overcome?
I can take that one maybe. So, Shansha, you want to go? Yeah, please, go ahead.
No, you can go first, yeah.
So I think, utility space is usually for the planning purposes is using legacy tool. And I don't want to name specific ones, but people know what those are. And we have great experience with those. Those are great tools. But when we talk about optimization, this is something that really cannot reside in those environments. So our process, the reason we had to move process out of legacy tools and do it with the help of Gurobi is for the reason that the problem statement is too complex. The tools cannot handle it. And I think that utilities are slowly but surely coming to a realization that there are tasks and processes where you want to use legacy tools, and then there are some tasks and processes where you may have to use some of the, special tools called or solutions. And we've done both. So we work with utilities. We have really great relationships with many utilities in the US. We are even helping them today improve their process with existing tools. But slowly but surely, the gaps are being transparent for utilities, and they're converging towards using tools that I think we mentioned some of those today.
All right, guys. Well, I'm afraid we have run out of time. For those questions that we did not answer, we'll be getting back to you by email. This concludes today's presentation. On behalf of Utility Analytics Institute, I'd like to thank our panelists for the discussion day, Gurobi Optimization and Quanta Technology for sponsoring today's webinar, and of course you for joining. We hope you have a great rest of your day.
Thank you. Thank you, everyone.
Thank you.
Bye.
Thank you, everyone.